Hello students and welcome to my channel Maths Hub. So in this video, I will be telling you about the diagonalization of matrices. Now what do you understand by diagonalization of matrices? You must have an idea that what is a diagonal matrix. So a diagonal matrix is a matrix in which we have entries only on the diagonals and the rest all the non-diagonal elements are zero. So if any given matrix is given to you, then from that general matrix, how do you convert it into a diagonal matrix? So if you have seen my last videos, you might be well aware of the topic eigenvalues and eigenvectors. So we will be using that concept to convert any general matrix to a diagonalized matrix, right? So what is the diagonalization of a matrix? It is the matrix, as I just said. A diagonal matrix is a matrix where the diagonal elements are the eigenvalues. So when we will compute it, you will find that all the non-diagonal entries are becoming zero and all the diagonal elements are same as your eigenvalues, right? So how do we get all these things? So for that we require a modal matrix, and a modal matrix is just a matrix whose columns are simply the eigenvectors that we obtain by solving the eigenvalues, right? So that modal matrix is denoted by the matrix E. So what are the steps to diagonalize a matrix? The steps are, the first step is, whatever the general matrix is given to us, we denote that matrix by A and we calculate the eigenvalues of that matrix, right? The second step is, for every eigenvalue, we calculate its eigenvector. And then in step 3, we form the modal matrix by putting the eigenvectors in the columns. And after we get modal matrix P, we find out P inverse. So you can calculate P inverse by any method. So far we have discussed the Gauss-Jordan method. We have discussed Cayley-Hamilton theorem to calculate the inverse, or you can use the method of adjoint, right? So you can calculate P inverse by any method. And once we calculate P inverse, how to get the diagonalized matrix? We will take P inverse, A and P will multiply these three matrices, and after multiplying them, whatever matrix you get, that will be a diagonalized matrix, right? So before we go into the questions of solving the diagonalization of a matrix, let us see few results which are very, very important while you are diagonalizing a matrix. So the first result is that if we have a n cross n matrix with n distinct eigenvalues, then it is always diagonalizable, right? So if the order of the matrix is n and we are getting n distinct eigenvalues, then it is always diagonalizable. Then let's see what are the rest of the notes. Now, if there are no repeated eigenvalues, the diagonalization is still guaranteed, right? That means it is not necessary that it has to be distinct. If there are, suppose, all distinct eigenvalues, then it is not necessary that diagonalization is always guaranteed. It is not always true, but you can say that it is possible, right? Then the presence of repeated eigenvalues immediately does not mean that diagonalization fails. So suppose if I get my eigenvalues as 1, 1, 2. So here the two eigenvalues, they are repeating. That doesn't mean that this matrix is not diagonalizable. There may be both the cases. It might be diagonalizable, it might not be diagonalizable. So we have to check its eigenvectors. Third is, if you can get enough linearly independent eigenvectors from the repeated eigenvalues, then we can still diagonalize, right? Now, it might happen that for these two eigenvalues, we only get a single eigenvector, right? So in that case, diagonalization is not possible. But for the each values of eigenvalues, if I get one eigenvector, then diagonalization is possible, right? So for example, suppose there is a 3 cross 3 matrix whose eigenvalues are 2, 2 and 4. If we can get two linearly independent eigenvectors for the eigenvalue 2, then it is diagonalizable, right? But anyhow, if the eigenvalue of 2 gives only one eigenvector, then diagonalization fails, right? Okay. So now let us try to work out these problems of how to convert a general matrix to a diagonalized matrix. So let's see. The first exercise says that diagonalize A equal to 5105 if possible, right? So the first step is that we have to calculate the eigenvalues of this matrix. So we know that how to calculate the eigenvalues. We will take A minus lambda I matrix and we will put it equal to 0. So in this case, we have 5 minus lambda, 1, 0, and we have 5 minus lambda. Let's put it equal to 0. So now when we solve this determinant, we get 5 minus lambda squared minus 0 is equal to 0. So when we solve this, we get the two eigenvalues as 5, 5. Now for these two eigenvalues, if I get two different eigenvectors, then diagonalization will be possible. And if I don't get two different eigenvectors, then it is not possible. So let us take the case lambda equal to 5 and let us calculate the eigenvector corresponding to this eigenvalue. So to get the eigenvectors, we will have A minus lambda I multiplied by x equal to 0 and we need to calculate this x. So let's substitute in this vector lambda equal to 5. So we will get 0, 1, 0, 0 and let the set of unknown vectors be x1, x2 equal to 0. So when I solve the first row, I get 0 into x1 plus 1 into x2 is equal to 0. That means x2 is equal to 0. So that means x1 is free, x1 can take any value. So we get the vector x1 and 0. So if I put x1, if I take the lowest vector, that becomes 1, 0. That means for the eigenvalue lambda equal to 5, I will be only getting one eigenvector. That is 1, 0, right? So this shows that diagonalization is not possible, right? Because I'm not able to construct the modal matrix. Clear? So now let's try another problem. So let's try this. We need to diagonalize 2, 3, 4, 1 if possible. So let's first of all find out the eigenvalues of this matrix. So we have 2 minus lambda, then we have 3, then we have 4, and then we have 1 minus lambda. And let us take its determinant equal to 0. So we have 2 minus lambda into 1 minus lambda minus 12 is equal to 0. So from here we get 2 minus 3 lambda plus lambda square minus 12 is equal to 0. So that turns out to be lambda square minus 3 lambda minus 10 is equal to 0. So you get lambda square minus 5 lambda plus 2 lambda minus 10 is equal to 0. So that gives rise to two factors, lambda minus 5 and lambda plus 2 is equal to 0, right? So from here, the values of lambda become 5 and minus 2. So now let us try to calculate the eigenvectors corresponding to lambda equal to 5 and lambda equal to minus 2. So for lambda equal to 5, we get the matrix 2 minus 5 is minus 3, then 3 here, 4, 1 minus 5 is minus 4, and the system of unknown variables are x1 and x2 equal to 0. So you can see that both the equations will give rise to the same equation, right? So we can say minus 3x1 plus 3x2 is equal to 0. So in this case, we say that x1 is equal to x2. So in this case, I get the eigenvector as 1, 1. So now let's try for lambda equal to minus 2. So for lambda equal to minus 2, we get the vector, the matrix 2 minus minus 2 is 4, 3, and then we have 4 and 3 over here. So again, you can see that both the rows will give rise to the same equation. So we have 4x1 minus 3 plus 3x1 is equal, x2 is equal to 0. So that gives us 4x1 is equal to minus 3x2, right? So from here, if I put x2 is equal to 4k, then x1 will come out to be minus 3k, isn't it? Right. So my vector becomes minus 3 comma 4. This is my vector, right? So this leads to the modal matrix. So now we are in a situation to calculate the modal matrix. So how to calculate the modal matrix? Whatever are the eigenvectors that we obtain, we put the eigenvectors in the form of columns. So the first eigenvector placed here, the second eigenvector placed over here, right? So let's try to calculate the inverse. So inverse is determinant 1 by the determinant into the adjoint. So we have plus, minus, plus, minus. What is the determinant? 4 minus minus 3, so it is 1 by 7. And then we have 4 over here. Then we have 1 over here, minus 3 over here, and then 1 over here. So that leads to 1 by 7. Let's take the transpose. So it is 4 minus 1 minus 3 minus 1, right? So now finally, what is the diagonalized matrix? The diagonalized matrix is P inverse AP. So that is 1 by 7, 4 minus 3 minus 1 minus 1 multiplied by A, that is 2, 3, 4, 1 multiplied by the matrix P. P matrix is 1, 1, minus 3 and 4, right? So let's try to multiply all these matrices and let's see what is the final product. So let me multiply the first two matrices and then we will see what is its results. I'll write the answer somewhere over here, right? So I'll write the answer over here. So 4 into 2 is 8 minus 3, first row with the first column. So 4 into 2, 8, minus 3 plus 4 is minus 12. So I'll get here a minus 4. Then the first row multiplied with the second column. So that leads to 4 into 3, 12, minus 3, that is 9. Then we have the second row multiplied by the first column. Minus 1 into 2 is minus 2 and then minus 4. So we get a minus 6 over here. Then minus 1 into 3 is minus 3, minus 1. So that leads to minus 4, right? And then we multiply with 1, minus 3, 1 and 4. So that is giving rise to minus 4 into 1 is minus 4 plus 9. So that becomes 5. Then we have minus 4 and minus 3, 12 plus 36. So that is 6, 7, 8, 48 over here. Then we have minus 6 into 1 is minus 6, minus 4 is minus 12, and then we have minus 6 and minus 3, 18, minus 16, that is 2 over here, right? So we just need to check out this matrix. Are all the calculations done correctly? Minus 3 and minus 4. So we have the modal matrix 1, 1, minus 3, 4. P inverse is something like, so here there is a mistake. So this sign should be a minus sign over here, and this should be a plus sign over here, right? So just check this. Now, for when we calculate the minor, it will become minus 3, and when we calculate the minor here, it will be plus 1. So this leads to 4 minus 1. This will be plus 3, and this will be plus 1, right? So just excuse me for this error. So we have 4 plus 3 minus 1 plus 1 over here. This is the error, that is not giving you the correct answer, that is why. So now let us multiply them, right? So what are we supposed to get here? Let's see. Right. So now we have 4 into 2, 8. 8 plus 12, 20. Then we have 4 into 3, 12 plus 3, that is 15 over here. Then we have minus 3, minus 2 plus 4, 2. Then we have minus 3 plus 1, minus 2. And then we multiply with this matrix. So what do we finally get? 20 plus 15 is 35. Then minus 60 plus 60 is 0 over here. 2 minus 2, 0 over here. Minus 6 and minus 8 is minus 14, right? So now when I substitute here, I'll get 35, 0, and I get 0 minus 14 over here. When I divide by 7, I get 5, 0, 0, minus 2. So in the very beginning, when I told you that what is diagonalization, I said that any general matrix can be converted to a diagonalized matrix. So a diagonalized matrix is when the diagonal entries, we are having some non-zero values, and all the non-diagonal entries, they are becoming 0, right? So here you can, another interesting feature is that the non-diagonal elements are 0. The diagonal elements are exactly the eigenvalues of your matrix, right? So we had lambda equal to 5 and lambda equal to minus 2. So if you check that this was the eigenvector corresponding to lambda equal to 5, and this was the eigenvector corresponding to lambda equal to minus 2. So the way you have placed the modal matrix, in the same position you will find the eigenvalues. So this becomes your diagonalized matrix, right? So just try this exercise. This is a 3 cross 3 matrix. So you will get 3 eigenvalues and check whether you get an eigenvector corresponding to each eigenvalue. So if you are able to find out an eigenvector corresponding to each eigenvalue, this matrix will be diagonalizable. Otherwise, it won't, right? And if you just try problems from other books also. So if you have any doubt, do let me know in the comment section. And thank you so much for watching the videos. If you like the video, do hit the like button. And those of you who have not subscribed my channel, do subscribe my channel to get the latest updated video, right? So believe in yourself and you will definitely succeed. Thank you so much.